In lecture 2, we're going to talk about normal statistics. So this is following up a little bit on some of the topics that we ended with last time. So last time we had a result that we stated near the end that if we have a random sample, some xn's, and they are IID from some PDF, some distribution f. Then, if I look at the moment generating function of x bar, so mgf of x bar at t, this is the moment generating function of any of them. I'll pick one, but they're all the same, evaluated at t over n to the nth power. So again, capital N here is my sample size, right? I have random variables x1 to xn, IID from some distribution, right? This is why I can write x1 here, because m of x1 is the same thing as m of x2 is the same thing as m of x3, etc., right? They all have the same distribution. They all have the same MGF. There's other ways to write this. This is a common way of writing it. Point being is that if I have a random sample, the MGF of the arithmetic mean has a pretty simple form. So if I know the MGF from underlying data, I can derive the MGF of x bar. So the theorem that we stated last time, which leads into today's lecture on normal statistics, or statistics for normal data, is that if my data comes specifically from a normal distribution, let's say normal mu sigma squared, then x bar, my arithmetic mean, will have a normal distribution with a mean mu and a variance sigma squared over n. So this is something that you may have seen, for example, in an introductory statistics course, and this is the proof, right? This theorem, this result that I stated, we proved the result. This is why it's true. But this theorem, or this first result up here, I'll put a star next to it, applies to any kind of random variable. And the world doesn't exist entirely of just normal data. There's lots of other types of data. So, for example, we can pick something more obscure. Maybe my data comes from a gamma distribution. So the gamma distribution has two parameters, alpha and beta. If you remember, I'll write on the side here, the PDF of a gamma, it is a continuous random variable. The PDF is beta to the alpha, x to the alpha minus 1, e to the negative beta x, all over gamma of alpha. And in the past, we may have written something like 4x bigger than 0. That's okay. In this course, I'm going to try and train you to write this a little bit differently. And I'm going to try and train you to write these with indicator functions. So I could multiply by the indicator that x is bigger than 0. So it's indicator again. You'll get used to them. Indicator that x bigger than 0 is simply going to produce a 1 when x is bigger than 0 and 0 when x is less than or equal to 0. We'll see probably next lecture why these are very useful and they can help us. Basically, they can allow us to write it out all in one line. We don't have to write for x bigger than 0. And this can be helpful in algebraic manipulations down the line. So this is a gamma distribution. A gamma distribution is a bit like an exponential distribution. So here's maybe an example of a gamma distribution. It has two parameters, alpha and beta. And I could say, well, maybe my data is positive. It's not normal. It can't take on a negative value. And maybe gamma is a good model for my data. And I might be interested in answering the question is, okay, what if I assume my data is from a gamma distribution? What is the distribution of x bar if I assume that's true? And our theorem comes to the rescue here because I can get the moment generating function of x bar. And if I know the moment generating function, I can maybe figure out what the distribution is, because the MGF is going to characterize my random variable. So our theorem says it's the moment generating function of any of them, evaluated at t over n to the nth power. Now you've got to remember what the MGF of a gamma is. So where do I want to put this? The MGF of a gamma has the following form. It's 1 minus t over beta to the negative alpha, as long as t is less than beta. So that's the MGF kind of generically of a gamma random variable. And so we can plug that into our formula, and we have 1 minus t over beta to the negative alpha. We should be careful, though, because instead of plugging in t, we're really plugging in t over n. So it should be t over n beta, or t over n over beta. And then this whole thing gets raised to the nth power. I can simplify a little bit. Let me just bring this nth power in. This would give me 1 over t n beta to the negative n alpha. So this is, if I just ask you what the MGF of x bar was, that's the answer. The MGF of x bar is 1 minus t over n beta to the negative n alpha. However, we might be able to recognize that this MGF is, we can recognize this as the MGF of another gamma distribution. We just need to specify what the parameters of the gamma distribution are. So how do I recognize this as the PDF of a gamma? It has a very similar form to this blue MGF up here. That MGF is 1 minus t over beta to the negative alpha. And this is similar, but instead of beta, it's n beta. Instead of alpha, it's n alpha. And so it's going to just be the MGF of a gamma n alpha n beta distribution. Another way to think about it is if I said my random variable is distributed gamma n alpha n beta, what would be the MGF? This is what I'd write down. And so what this tells us is that if x bar follows the MGF of a n alpha n beta random variable, then it must be that x bar follows a gamma, the corresponding distribution. X bar's distribution is n alpha n beta. So that's the example. You could do this with other distributions. You could pick your favorite, and you might be able to recognize the distribution of x bar. Not always, but sometimes. And this is nice because it allows us now, we're kind of expanding our world. Intro statistics gave this brute fact, if x's are normal, x bar is normal. But there's other types of data in the world, and there are other distributions, and the point of this class is to broaden the horizon and talk generally about statistics for any kind of distributions. We'll talk a little more about that at the end. For now, given that I've said that, let's go back and talk more about normal distributions. So here is kind of the main focus for this lecture. And I'm going to state a theorem here. And the theorem is going to assume that we have a random sample from some normal mu sigma squared distribution. And the statement of the theorem is that 3 things are going to be true. 1, what we wrote above is true. X bar is normally distributed with a mean mu and a variance sigma squared over n. The second fact is going to use the sample variance, s squared. or s squared on n minus 1. We talked a little bit about this last time. It's the traditional sample variance you learn in an introductory statistics course, which is 1 over n minus 1, and then I sum up the deviations, the xn's minus x bar, square them, I sum them up, divide through by n minus 1. Okay, so that, just remember that. And it turns out that if our data is normal, so this is the important assumption of the theorem is the data is normal. If the data is normal, x bar is independent of s squared. That's only true for normal random variables. The third fact tells us something about the distribution of s squared itself. So we like to say that s squared has some known distribution, has some nice distribution. The way that this is typically written is we have to properly scale it. So we're going to multiply by n minus 1 over sigma squared. If we multiply s squared by n minus 1 over sigma squared, turns out that this quantity has what's called a chi-squared distribution, which is denoted with a Greek chi, 2 for squared, and it has a parameter associated with it. And that parameter is called the degrees of freedom. And in this case, n minus 1 over sigma squared times s squared has a chi-squared distribution with n minus 1 degrees of freedom. So I'm going to just note this. This is a chi-squared distribution with n minus 1 degrees of freedom. We'll talk about this fact in a little more detail in a second. But that's the statement of the theorem. So we proved one. Fact one we proved at the end of last lecture. Fact two, let's hold off on this and do this in the future. There's a way to prove it now, but it's a bit complicated. There's going to be a really easy way to show this in the future. So right now we're going to take it as a brute fact. If the data is normal, x bar and s squared are independent. Fact three, let's just do a sketch here of this proof. We're going to do a really high-level sketch, and the only reason we're going to do it is because it tells us something about this degrees of freedom parameter. So let's talk about, before we get to that kind of high-level sketch, let's talk about this third fact, because we haven't talked about the chi-squared distribution yet. So the fact here, we'll rewrite it, is that n minus 1 over sigma squared times s squared. I'm going to drop the n minus 1 there because I'm lazy. Has a chi-squared distribution with n minus 1 degrees of freedom. So let's talk about the chi-squared distribution. So the chi-squared distribution has a parameter. And we'll denote it with k. It's called the degrees of freedom. And the chi-squared distribution has a PDF, is a continuous random variable. Has a PDF given to us as 1 over 2 to the k over 2, gamma of k over 2, times x to the k over 2 minus 1, e to the negative x over 2. And this is true for positive values of x. Or maybe I should follow my own advice and write this with an indicator function. Indicator, x is bigger than 0. So it's a positive random variable, which makes sense. S squared is squared. It should be positive. And it turns out that this is just a special type of a gamma PDF. It's just a special case of a gamma. It's a gamma random variable where alpha is degrees of freedom over 2 and beta is a half. So let's say gamma this, it's the PDF of that. That's what that PDF is. So it's a particular positive random variable. So if this is 0, maybe our chi-squared looks something like that. Maybe that's if this is our f of x and this is x. It'll look something like that. It's a gamma. We talked about those already a little bit. So some other important facts, and these are facts I'm not going to prove, but facts you should know and commit to memory. So that's true of this previous theorem. Never going to ask you for a proof of it. You should know these facts. So some facts about the chi-squared distribution. Where does this come from? Right, so apparently it's an important distribution because it is related to s squared here. It's related to our sample variance. If I have z, so let me write this down here as fact number 1. If I have a random variable z, and it has a standard normal distribution, then z squared has a chi-squared distribution with 1 degree of freedom. Second fact, let's keep it in green. Second fact is that second fact. Let's make this 2. Second fact is that if I have a bunch of well, that's interesting that got inserted. What did I do? Back up here. Undo. Okay. Second fact is that if I have a bunch of standard normal, say a random sample of standard normal random variables, if I look at the sum of these, of the squares of these, this is going to have a chi-squared distribution with n degrees of freedom. So the more general fact, we can write this as fact 3, is that if I have, let's say, a1 to an, and these are going to be independent random variables, and they're going to be chi-squared random variables, and they're going to have potentially different degrees of freedom. So I'm going to have a potentially different degree of freedom for each of these. So let me write it this way. Let's write it this way. Let's say we have a series of ANs. They are IID, chi-squared of KN. So A1 is chi-squared, not IID, independent. Sorry about that. So A1 is chi-squared with 1 degree of freedom. A2 is chi-squared with 2 degrees, with k2 degrees of freedom, a3 is chi-squared k3 degrees of freedom. Then if I sum these up, I sum up my an, these are going to have a chi-squared distribution, and the degrees of freedom is going to be the sum of the degrees of freedom. So it's a bit abstract. For example, if A1 is chi-squared of 3 and A2 is distributed chi-squared of 1.7, degrees of freedom doesn't have to be an integer, then A1 plus A2, as long as these things are independent of each other, this will have a chi-squared of what? 4.7? So that's kind of the fact I have written here. You can summarize this in words by saying that the sum of independent chi-squared is also chi-squared with a degrees of freedom equal to the sum of the degrees of freedoms. The sum of independent chi-squareds are chi-squareds. They have to be independent. But the sum of independent chi-squareds are chi-squareds, and the degrees of freedom of the resulting chi-squared is just the sum of the degrees of freedom. So that's so my little example 2. It's true generally. If I have a bunch of them that are independent and I sum them up, it's still chi-squared. This is where you can basically use fact 3 to prove fact 2. Right? So basically, if I believe fact 1, and then if I have a bunch of standard normals that are independent, that are independent, then if I square them, these are all chi-squared on 1, and so if I sum them up, they're chi-squared on n. So just a couple facts. Basically, square a standard normal, you get a chi-squared. You sum up independent chi-squared, you get another chi-squared, and you sum the degrees of freedom. So they behave pretty nicely. So where does this come into things? Note that if I look at my formula for s squared, it's basically, this is my formula, right? And so we're going to say it's something like the sum of some z squares. Maybe? Kind of? Not exactly, but kinda. This at least gives you some intuition for why it makes sense that s squared should have a chi-squared distribution. Because if the x's, these little x's are normal, and we can kind of fudge it and pretend that x minus x bar is normal. It's a whole other discussion. It's kind of like a sum of square of normal things. And so you would kind of expect it to follow rule 2. The problem is that you would expect this sum of these things to be chi-squared on n degrees of freedom. But if we look at our theorem, s squared is this n minus 1 over sigma squared times s squared is chi-squared on n minus 1 degrees of freedom. So there's always this mysterious n minus 1, right? And we can give a little bit of a deeper look at why that exists and where that n minus 1 comes from. So this is kind of for fun, let's say. If you don't like fun, i.e. linear algebra, you can skip this. But just for fun, let's say not required to know. And I'm going to give a real high-level sketch of this whole thing. So it turns out that, let's just assume to make our lives easier, that mu is 0 and sigma squared is 1. So we have standard normal random variables. So this is basically talking about a proof of of claim 3 here. Okay, so this is claim 3 above. And let's just, we're not even get into the complications of if mu is, if we don't have standard normal. Assume we kind of have standard normal random variables. If that were true, what we would be able to do is form a matrix that looks as the following. On the main diagonal, it would have 1 minus 1 over n. And on the off the diagonal, it would have negative 1 over n. And we could call this the kind of residualizing matrix. And the idea basically being that this matrix is going to residualize our x's. It's a fancy little matrix. What you can show about this thing is that the rank of it, of this residualizing matrix, is n minus 1. Not going to prove that. We'll take it on faith here. Turns out this residualizing matrix can be used to make s squared. And the way it's used is that if I take my vector of random variables, x tilde, and I look at x tilde transpose a x tilde, this is what's called a quadratic form, this is going to give me n minus 1 times s squared. We're ignoring any kind of sigma squared at this point. And it turns out that this kind of quadratic form has a chi-squared distribution if my x's, let's say if x is normal, my x's are normal, and I look at, so if I have a vector of normal random variables, and I look at x transpose ax, it's called a quadratic form, this thing will have, as long as a is nice enough, a chi-squared distribution, and the degrees of freedom will be the rank of that matrix. In this case, the rank of the matrix is n minus 1, and that's basically the proof. So we're done with fun for now. Beyond the scope of this course, you don't need to know that, but it gives you a sense of where do we get n minus 1. So if I go back up to my theorem here, where do we get, why is it n minus 1 degrees of freedom? It's because you can basically look at s squared as a quadratic form with a certain matrix, and the rank of the matrix is n minus 1. There's a certain subspace with dimension n minus 1. So it has to do with the geometry of the s squared kind of linear or quadratic operator. So it's a pretty deep point. Beyond the scope of the course, what isn't beyond the scope of the course are these facts. So I'm just going to say, know these. So we can look at some other related quantities. And so you may have seen some of these, say, in an introductory statistics course. And one thing we want to look at is called the t-distribution. So the t-distribution has, again, one parameter. We'll call it k, and this parameter is also called the degrees of freedom. And it's going to be very intimately related to the degrees of freedom for a chi-squared. So the t-distribution looks like a normal. So let's say this is our standard normal distribution. A t-distribution might look something like this. What is said about t-distribution is that it has fatter tails. That is, the normal distribution decays exponentially as we go to positive and negative infinity. It goes close to 0, kind of exponentially fast. The t-distribution goes to 0 polynomially fast, so much slower. And so the t-distribution has kind of more probability further from 0. Say more probability in the tails, which means we are more likely to get a more extreme observation under a t-distribution than a normal distribution. Now, t-distributions have a PDF, so we can write out the PDF. It's pretty awful, and I'm not going to lie to you. I have to look up what the PDF of a t-distribution is. I'm going to write it down. Hopefully you will then immediately forget the PDF of the t. Don't memorize it. You don't need to memorize it. There it is. I'm going to write it. It's pretty ugly, just to convince you you don't want to know it. Nobody knows t-distributions based on the PDF. The reason we know t-distributions is the following fact. We could maybe call it a theorem. Theorem's a big word. Fact only has 4 letters. So if I have, let's call it u, and u is going to be a standard normal random variable, right? So today we're talking about normal statistics. And if v has our new favorite chi-squared distribution, and we're going to say has some degrees of freedom, k. Let's assume that u is independent of v. U is standard normal, v is chi-squared, and u and v are independent. If I form the quantity, we can say if this is true, if I form the quantity u over v, square root of v over k, this has a t-distribution with k degrees of freedom. So I'll denote that as t paren k. So this is why we care about it. Well, almost why we care about it. Why do we really care about it? So that's interesting. We really care about it because if I have my underlying data, getting back to our random sample, if my random sample comes from a normal distribution, our first fact above is that x bar is also normal, has the same mean mu, and has a variance sigma squared over n. If I have normal data like this, I could form u as x bar minus mu over sigma over square root of n. This is going to have a normal 0, 1 distribution. Why do I know that? Well, x bar has a normal distribution, and all I'm doing is subtracting stuff from x bar and dividing through x bar by quantities, right? These are all constants. Mu is a constant, sigma is a constant, n is a constant. And I can linearly transform, say, a normal random variable, x bar, without, and it will stay normal, right? It's easy enough to show that the expected value of mu is, well, I can just pull out the 1 over sigma over root n, and I just get the expected value of x bar minus mu, which is surely 0. And I can show that the variance of mu is, again, I can pull out, in this case, I have to square everything. So it's sigma squared over now n. And I can ignore the mu, because that's just an additive shift that doesn't change my variance. I get times the variance of x bar, and that gives me 1, because the variance of x bar is sigma squared over n. So u, if I form it this way, is standard normal. Great. V, I'm going to use the other part of my theorem. I'm going to say it's n minus 1 over sigma squared times s squared. And if you believe the theorem, and I gave a sketch that I'm sure no one wanted to listen to, this is chi-squared on n minus 1 degrees of freedom. And what I wrote above here is u is normal 0, 1, v is this. We need independence. But wait, we have a theorem. Our theorem says that x bar and s squared are independent. Ain't that nice? So we also know u and v are independent. U is just a function of x bar, v is just a function of s squared. If x bar and s squared are independent, any functions of them are independent. So these two things are independent. This means that u over square root of v over, well, what's our degrees of freedom? N minus 1. So above I had written k, but here our k is n minus 1. So I divide through by n minus 1. This thing should have a t distribution. Before we write that down, let's just do a little bit of simplification, right? So the top here is x bar minus mu over sigma over square root of n. The bottom here is the square root of n minus 1 s squared over sigma squared, all of that over n minus 1. So look what happens. N minus 1 cancels. That sigma cancels with the square root of sigma squared. And what we're going to be left with here is x bar minus mu over square root of s squared, let's just call that s, divided by the square root of n. Our claim is that that's t distribution on n minus 1 degrees of freedom, right? This is what this theorem, or this fact, said. Since all the conditions are met, that is a t distribution on n minus 1 degrees of freedom. You may recognize this quantity from intro statistics. This is basically a t-test. And this is where at least part of the theory of a t-test comes from. We'll get to actual hypothesis testing, hopefully at the end of this course, time permitting. But that's a big chunk of the theory. So that's kind of a cute little fact. Notice that we got rid of any of sigma squared. We basically replace it with an estimate s, which is quite nice. So that's some normal statistics. Let me just do a real quick recap of this. So we have this. We started off with this theorem about moment-generating functions of x bar. You can use that generally. It proves the first fact that our kind of three-part theorem you should memorize. X bar is normal. Divide through the variance by n. Our second fact is that x bar is independent of the sample variance. And the third fact is that if we scale our sample variance correctly, it has a chi-squared distribution. So this chi-squared distribution is some kind of positively distributed random variable. Chi-squareds have a couple facts. The most important fact being, or facts being, that if you square a standard normal, that's a chi-squared with 1 degree of freedom. And if you sum independent chi-squareds, you sum their degrees of freedom. This can also be used to derive things like the t distribution. This is our kind of theorem about the t, probably less important to memorize. And it allows us to derive our t statistic, which is basically this quantity here. And the t statistic indeed has a, quote, t distribution. So that's kind of enough for normal random variables. We want to talk more generally now about statistics. And so I want to talk a little bit about the philosophy of statistics for a couple minutes here. We've all taken now probability, 451. And in probability, you might be given something like this. So I'm going to say my xn's are distributed following, maybe as their IID, following some distribution f. And it might be that f has a parameter. So this is maybe some parameter. For example, normal distribution of mu and sigma squared, Poisson has a lambda, exponentially has this parameter lambda, gamma has alpha and beta. And in probability, what they'll say is we know theta equals maybe 5. Maybe theta is 5. Calculate the probability of something that, xn equals blah, blah, blah. So that's basically the viewpoint of probability. I'm going to tell you what the distribution of the random variables are. Then I'm going to ask you to calculate something about those random variables. Statistics plays the game a little bit differently. Statistics would say, okay, we're going to start off again saying we have a random sample. Maybe it's from some distribution, and that distribution has a parameter theta. We don't know theta. That's the problem with statistics. Maybe we know something about theta. Maybe it's positive. Maybe it has to be between 1 and 10. What we want to do, we want to use my samples to estimate theta. Maybe we want to know how confident are we in our estimates? So, for example, maybe I have data comes from a normal distribution. Maybe I know that the variance is 1. How do we estimate mu? X bar? That seems like a good estimate. What are the properties of X bar? Well, we know something about its distribution. We know something about it's independent of S squared. But what if I have some more general problem? What if I say something that's not normal? Maybe my data has an exponential distribution. Maybe the data represents failure times for components in a car. And so I know it has an exponential distribution, has some unknown parameter lambda. Lambda has to be positive. How do I estimate lambda? If I told you the data is normal and I want to estimate this mean mu, people are going to tell me to use X bar. If I tell you the data is exponential and I want to estimate lambda, what do we do there? What's the general approach? Are there general approaches to this? That's what this course is about. What are the general approaches to forming estimates of arbitrary parameters given data coming from some distribution? How do I evaluate these estimators? How do I find good ones? What are the properties of these? So that's basically what our course is going to be about. What I want to finish off the lecture with today, what we're going to be working with in statistics is families of distributions. Let me write that down. We'll work with families of parameterized distributions. For example, we're going to work with, normal distributions, mean mu, sigma squared, where, mu is any real number and sigma squared has to be positive. Or, I'll work with exponential family random variables where lambda is bigger than 0. Or I'll work with uniform random variables between 0 and some theta, and maybe theta, I don't know, maybe theta is between 10 and 20. So there's lots of different ways of modeling data. As an applied statistician, basically what you do is if you want to solve a problem, you try to choose a distribution and a range of parameters associated with the distribution to try and model the data. And then you can try and estimate parameters of that, and maybe the parameters tell you something about the data or the model generating process. Maybe the parameters are slopes in a regression. So regression can be cast as basically an estimation problem. Maybe they are probabilities in some machine learning algorithm that can be cast as a estimation problem. So we're going to be working with basically the way we're going to set up our problems is we're going to say our data comes from some distribution, some family of distributions with some parameter. We don't know what the parameter is. Maybe we know something about where the parameter lives. We know it's positive. We know it's between 10 and 20. And we're going to try and estimate it. One of the most important families, and this is a big family of distributions, is called the exponential family of distributions. So let's talk about the exponential family. And specifically, we're going to be talking about the one parameter, or maybe I should say one-dimensional we're going to try and avoid talking about having to estimate multiple parameters in this course. We may touch on it a little bit for fun at various points. The exponential family turns out is a really useful set of probability distributions. And it's a set of probability distributions that you already know many of them, and they're many of your favorite probability distributions. So I'm going to write out kind of what the definition is. It's going to seem quite strange, but we'll talk about some examples, and it's not nearly as scary as it might seem. So let's assume we have a parameter, theta, and theta is going to live in some bigger set. Let's call it capital theta. We have a parameter theta. It lives in some bigger set theta, capital theta. And the data, the x of n's, are a random sample from f parameterized by some parameter theta, where our joint distribution has the following form. It can be written as a function h that depends on my x's, but not theta, a function c that depends on theta, but not the data, times the exponent of, or the exponential of, a function t that depends on the data, but not theta, and a function w that depends on theta, but not the data. So we have some data. It comes from one of, we don't know which, but some distribution f, parameterized by a parameter theta. Theta lives in some bigger set, whatever. The PDF, let's say the joint PDF of these x's, has the following form. It is a function h that depends on the data, multiplied by some function c that doesn't depend on the data, it depends on the parameters, times the exponent of a similar kind of situation. Exponent of some t that depends on the data, not theta, and some w that depends on theta, not the data. So h and t depend on data, not theta, and c and w are the reverse, depend on theta, not data. So this seems like a very strange setup. But we actually have seen many of the kind of familiar distributions that we have are exponential families. Example, Poisson. The Poisson, I guess I didn't finish this sentence. So if we have this, we call the family of distributions an exponential family. So we have this stuff, this data comes from some distribution f of theta. If I look at the joint distribution, the joint can be written in a specific way. And it's we're going to have to figure out what exactly h, c, t, and w are. But if we can find some h, c, t, and w such that we can write the PDF in this form, we call it an exponential family. Turns out these exponential families have a ton of super nice properties. Finding good estimators for them, no problem. Things aren't exponential families, could be a little more difficult. So let's just look at an example to make this concrete, because it's a bit abstract. Poisson, right? So let's assume my data comes from a Poisson distribution, has some unknown parameter lambda. Lambda's positive. Okay. So instead of theta, I have lambda. All right. The joint distribution of my data, let's write it out. Fx, it's the product of my marginals, and the marginals marginally follow Poisson, right? So it's lambda to the x of n, x of n, e to the negative lambda over x n factorial, right? That's what each of the marginals are, and if I want the joint, I just multiply them all together because they're independent. I can simplify this somewhat. I'm not going to be able to simplify these factorials much. So it's just like the product of 1 over xn factorial over all the n's. But this other part here, I can simplify. The product of lambda to xn is lambda to the sum of the x of n's, right? So the reason for that is that right? So basically I have lambda to the x1 times lambda to the x2 times lambda x3 times lambda xn. I can always rewrite this as lambda to the x1 plus x2 plus plus xn, right? So it's lambda to the sum of the x of n's. I'll be a little lazy with my indices. And then I have n copies of e to the negative lambda. That's e to the negative n lambda. Okay. It doesn't quite look like an exponential family. What I have to do is I have to find h, c, t, and w to make this true. I'm going to pull one more trick, which is we have to remember that if I say e to the log of some quantity a, that's the same thing as a, right? Because exponent and log undo each other. So I could write, let's bring this over here. So I have my part that depends on these factorials, that's ugly. I could rewrite this lambda to the sum as e, the exponent of log of lambda to the sum And then, of course, I have my e to the negative n lambda, right? And, of course, if I have a log, I can bring the exponent down. So, again, I have my ugly part depending on factorials. exp, I can bring this sum out, right? Because that's just like an exponent rule. The other exponent rule is that what log of a to the b is b log a, right? I'll still be left with a log of lambda in here. And I have my e to the negative n lambda. My claim is that this family of distributions is an exponential family. It means what I have to do to prove that is I have to find h, c, t, and w. And I've tried to basically put it in a form where I can do that. Let us call this thing h. That thing depends on x's in a complicated way, but it doesn't depend on lambda, which is my parameter in this case. This thing I could call c of lambda. This thing depends on the parameter, but there's no x's in here. And then I have exponential. And so if I have my c, have my h, what's left, have c, have h, better be a t and better be a w. Well, that sure looks like a t. And that sure looks like a w. That sum of x's depends on the x's, not the parameter. And log of lambda depends on the parameter, but not the data. So basically, if I can claim and say h is this, c is this, t is this, w is this, look, the joint distribution of my data has the form. You could move c over here if you wanted to, it doesn't really matter. And so it is an exponential family. So let's say this is an exponential family. Let's do another real quick example. Well, what if my data comes from an exponential distribution? There's a difference between an exponential family, which includes things like Poisson, and the exponential distribution. Not surprisingly, the exponential distribution is an exponential family. Let's prove it. How do I prove it? I gotta prove to me that I can do this factorization, or I can do this writing it in this form. I can find an h, a c, a t, and w, so that the joint PDF can be written in this form. So again, let's write out, I'm going to speed up a little bit here. fx, right, it's parameterized by some parameter lambda, is the product of all my marginals. What's the distribution of an exponential? It's lambda e to the negative lambda x n. Now, I should be a bit careful because exponentials have to be positive. So I really should include an indicator function in here. I didn't do that with Poisson, but it can be forgiven. So here's where we're going to see why why indicator functions are dead seriously important, because you can get the wrong answer if you do this incorrectly. Okay, so I need to include my support somehow in my PDF, because I'm basically trying to factor out my PDF in a certain form, right? So I need to make sure I include that support. And I can include it by including an indicator function. It says that these x sub n should be positive. So, okay. So let's do this out. I can pull out this product of all these indicator functions. It's a mess. I mean, it's a complicated, messy function, but who cares? It's just a thing. Put it there, right? Pull that out. We have n multiples of lambda, so we'll have a lambda to the n. And then we'll have e to the negative lambda. And I think you'll believe me now that we'll have a sum of the x sub n's here again. And I can play this game again. So I have my product of my indicators out front. I have lambda to the n, and I can write this as e to the negative. Oh no, I don't even need to play any games here. It's already a super nice form. Not surprisingly, the exponential distribution is easy to show as an exponential family. So if I claim that this is t of x, depends on the data, not theta. This is w of lambda, depends on the parameter. Or I should probably include this negative in here. Depends on the parameter, not the data. This thing is c of lambda, and this thing is h of x. There we go. I've shown that I can factor in the right form. Ain't that nice? Not surprisingly, the exponential distribution is an exponential family. So this data is from an exponential family. These exponential families are going to make our lives really, really, really easy. If we know something is an exponential family, it's going to make things super easy. So you're going to learn to love them. Okay. There are other exponential families. I'm just going to write some out. I'm not going to prove them. You'll do some for homework. Poisson distribution is, we showed that the exponential is, normal is, yeah, let's just say normal is, gamma is, beta is, there are others. So what's left, right? We've listed so many of these. Let's look at data from a uniform distribution. So let's assume that we have data that is uniformly distributed between 0 and some unknown parameter theta. So our PDF will look like this. It's flat. It's at 1 over theta between 0 and theta, and it's 0 outside of that, right? So let's look at the joint distribution is product of our marginals. What are our marginals? It's just 1 over theta, right? But I need my support. Again, this is why indicator functions are going to be useful. You're going to hate them at first, but they're going to be useful. I need to encode my support. My support is that the x sub n's are between 0 and theta. Okay? So that is the proper way to encode that. 1 over theta for, indicator of the support. The support is x n's are between 0 and theta. So let's try and make this into the form of an exponential family. Certainly I can pull out this 1 over theta, so it's maybe 1 over theta to the n. And then I get left over here the product of all these indicator functions. In order to make this an exponential family, right, I have to write it as some function h that depends on the data, not theta, some function c, right? I have to write it as this form. This is not going to be possible. Why? Exponential families, basically, you need to be able to write it in terms of these two pairs of something involving the data times something just involving the parameter. And a product of those. I can't factor these as products. I'm going to make the claim that you can't factor that indicator function including x and theta. There's no way to tease that apart and write it as a product of something just involving x and something just involving theta. It just doesn't work. So that's the general truth, is that is that if you have an indicator function of something involving x's and the parameter, you're never going to be able to tease it apart as a product of two things, and therefore it's not going to be an exponential family. The useful way to put this, the reason we have x and theta in an indicator is that if my support depends on the unknown parameter. So in this case, my support is between 0 and theta. That depends on the parameter theta. It isn't an exponential family. So that's a super easy way to rule things out. None of the other distributions I listed up here, Poisson, exponential, normal, gamma, beta, the support of those don't depend on any parameters. And so they're exponential family. If the support depends on the parameters, you can't do that factorization. That's not going to be an exponential family. So this is just a great rule of thumb to rule things out. Typically, if the support doesn't, typically it is an exponential. Maybe not always, but good rule of thumb. So exponential families are really going to help us out. One thing that should be noted is that I'm just going to write this down as a theorem. It's not really that hard to show. It's quite easy to show. Be a good homework question. Is that if I have some x sub n's from some distribution f parameterized by an unknown parameter theta, and so marginally f of theta is an exponential family, right? So let me back up and explain what I mean by that. When I just gave you the definition of exponential family, I gave it in terms of the joint distribution. It turns out it doesn't matter. If marginally, the marginal distribution can do the same factorization, the joint can do a similar factorization, it's an exponential family, and vice versa. So when you're checking exponential families, you can either check the joint distribution or you can just check the marginal. So let me just write this down. If the IAD marginally is an exponential family, i.e., if the distribution was just one thing, not the joint, just one, can be written as, some c of theta, some h of x. Now x is only one thing; it's not a multivariable function. Times exponent of t of x times w of theta. Then, if I look at now the joint, so this is the marginal of one observation, and this is the joint of all of them. If the marginal can be factored in kind of this exponential family way, then the joint is an exponential family. Practical advice is that it's often easier to check just the univariate marginal than to actually form the whole joint and check it. So practical advice, just check the marginal of one observation. Okay, right, so let's do an example, right? So I went up to this exponential distribution. I had to write this product, and it's product, and I had to think about it, right? I can just check one exponential. I can just say this. So let me write this as an example. I could just say, let's say x is exponential lambda, then f of x would be lambda e to negative lambda x, indicator that x is bigger than 0, and clearly this can be written, this could be h of x, this could be c of lambda, this could be w of lambda, and x here is t of x, right? That's super quick to do, right? I can just look at it. I don't actually have to make the whole joint distribution by multiplying these together and doing algebra. So just check the marginal of one of them. If it's true, it's going to be true for the joint. And it's not too hard. You should think about how to prove it. It's pretty straightforward. People talk about exponential families both ways, so it can get confusing. It doesn't matter. If it's true for the marginal, it's true for the joint. All that matters is you can do the factorization. I will typically state it in terms of the joint distribution, as I did here, where I defined it, but you can just check one of the marginals, and that's all right. It's good enough. All right, so I think that's probably, honestly, a good stopping point. So let's not force it to go on to the next topic. We'll save that for the next topic. But we can do a quick review of what we did today. Again, we talked about normal statistics. Talked about, let me put some stars here. Things you should remember, all right? So let's know that result. Definitely know this theorem, where we talked about the properties of normal, of x bar and s squared for normal samples. Definitely know these facts about chi-squares. You don't really need to memorize much about t's. They might come up. They're not that important. And definitely memorize the definition of an exponential family. That will come up. So next time, we're going to start talking a little bit more generally about statistics and kind of general properties of statistics. But we should leave it there. I think that's a great point to stop.